as a chemist, it's not very likely to get a plug and play type situation. So in order to see in this flask exactly my concentrations of everything is not very easy to do. And so in reality, chemists have to use these things called ice tables before they can do a plug and play. So I'm going to navigate through you what an ice table is and how to set it up. And but that's why it's useful to us, because I know how much as a chemist I put into the flask. Okay, so it takes a while for something to establish equilibrium. So let's say in the lab, I'd like to add some chlorine and some fluorine, and I'm going to make this fluorine hexachloride. Okay. So I put into my flask, I know this because I've got a clear bottle that's got nothing in it, and I dump in 6 moles per liter of chlorine, and I dump in 2 moles per liter of fluorine, and I put the cap on, and it's Friday, I put it to the side, and I go out for the weekend, right? And I have a nice weekend, and I work in my garden, and blah, blah, blah. And then I come back on Monday and the equilibrium has established. I've got tons of products being made and tons of reactants, and it's a little bit like a bathtub sloshed together. So I've chucked all this stuff into one end of the bathtub and it sloshes back and forth and back until eventually it reaches one solid level, one clear level, and that's equilibrium. And it's still like a convection current is still happening underneath. So my hot is still rising and my cool is still falling, right, in a bathtub. So even though the level looks the same, there's still stuff happening underneath. So even though the equilibrium constant has been achieved, I still have the rate of the forward equaling the rate of the reverse. Okay, so my point is though, that I know I chucked this stuff in the flask and then I went away for the weekend. And then I can do some tests. There's lots of tests that you can do. There's lots of, there's a precipitation test, and there's this thing called a colorimeter or spectrometer, same word, but different, different word, but same machine. And I can put it in and I can see the concentration of one of the colored compounds that way, etc. Anyway, so I went away for the weekend, get back on Monday, and I can see that the concentration of my FCl7 is 1.5 moles per liter, but I don't know the concentration of my F2, and I don't know my concentration of my Cl2 at equilibrium. I only know that I have some of this and some of this, and I have exactly this amount of this. So if I were to do a plug and play, here's my expression. These are all gas, so I include them all. Products over reactants, here's my expression. If I were to do a plug and play, I only have one thing to plug in order to find my K value, right? What is the equilibrium expression for the following reaction? That's the question. So I have one value, but I still need these two, and I haven't got it. So because of that, I have to set up what's called an ice table. I stands for initial. I initially put this in. It started with this, and then it changed. Some of it reacted, some of it formed. And then I finally have my equilibrium concentrations after the weekend. So in order to do an ice table, there's quite a few steps. I always suggest that students put like this elementary school line there, because that's going to help us remember that we're going to add and subtract these columns like we're in elementary school and you have, 20 plus 3, elementary school line, 23. So that elementary school line like prompts us into our memory. It's a really good tool to use for your memory. Okay, so I started with this, and I started with none of that, and at the end I ended with this. But I know that they changed according to the coefficients. So the change is still stoichiometrically the same. So this is going to change on a ratio of 7 to 1 to 2. Okay, so 7 x's, 1 x, and 2 x's, that's going to change by. So hold on a minute. Let's just rewind a little bit. So this change column, I'm going to use my coefficients for, okay? So change and coefficient, it stands for the same thing. So if this started with 0 and ended with 1.5, first of all, I must have made some of it, right? And I must have reacted some of those in order to make it. So I'm reacting these, I'm just going to subtract them when I'm doing my elementary school stuff. And I'm making this, so I'm adding it. Okay, but how much did I make? Well, I started with 0, I ended it with 1.5, so I must have made 1.50 moles per liter, right? Must have, because 0 plus 1.5 equals 1.5. So if I made 1.5 of this, and this is all still stoichiometrically true, then this is going to be 1.50 times one of these for every two of these, right? One of these for every two of these. So I'm going to get half as much of this guy. If this guy is 1.5 and the ratio is 1 to, if the ratio is 1 to 2 and this is 1.5, then this must be 0.75, right? So I have 0.75 that this is going to change by. I'm going to use up. I'm changing this by 1.5, and this is going to change by 1.50 times 7 chlorines for every 2 fluorine tetrafluorides. So that ends up being 5.27. So I'm going to use up 5.27 moles per liter of this thing. Okay. So now you've got a bit lost in the math, and that's why we've got this elementary school line, because that's going to help us to remember to do some subtraction. Now I'm just grabbing another color of marker. Okay, so elementary school line says I started with 2, I changed it by 0.75. I don't like that marker. Where's my green marker? Oh, it's on the floor. I changed it by this. So I have 2 minus 0.75, right? And so 2 minus 0.75 is 1.25 moles per liter at equilibrium. So I added 2 to the flask. I used up 0.75 moles per liter of it in order to make this. And so I am left with 1.25 in my flask. Over here, I started with 6. I reacted 5.27 of it in order to make my product. And so I'm left with 0.75 moles per liter of that stuff. That must be a 5 there. Anyway. Okay, now I have everything in my equilibrium column. I have this value, and this value. And now I can plug and play because I have my equilibrium concentrations. So the only thing that can go in this expression are equilibrium concentrations in order to find my equilibrium constant. So I already had that one, but now I have these two. My chlorine is 0.75, and I'm going to square that, or no, times that to 7, and this is 1.25. And so tappity tap that in your calculator, and you should get 8.99 is my K value for this expression. Okay, this is a 5. I just misread my handwriting. Okay, so that is 2.5. Okay, so right? So this value is greater than 1. That tells me I have more products than I have reactants. So that tells me that this equilibrium lies more heavily on my products than it does on my reactants. Okay. All right, so this bathtub sloshing back and forth isn't perfectly even, but rather we have a bathtub on a slant where I have more products than reactants. I guess I have to go this way, hey? More products than reactants. Okay. Example number 2. So it takes a while to understand ice tables. You got to practice them, right? The plug and plays are the easy. Ice tables are standard of excellence questions. So here I have another reaction. All of these are gaseous states, and so I'm going to include them all in my expression because it's a homogeneous mixture. So my expression ends up being products over reactants, all of them in there. Awesome. If only I had everything for my equilibrium line here, but I don't have everything for my equilibrium line, so I can't plug it all in. I only have one of them, so I can't plug the rest in. And like I said before, it's more likely that I know what I put in the flask on Friday, went away for the weekend, came back on Monday, and my machines can tell me one of the concentrations at equilibrium after that weekend, not all of them. So therefore, as a chemist, I got to set up my ice table in order to then find the equilibriums at all of them, and then I can plug and play, do the easy thing. Okay, so again, my change column. So this elementary school line, to remind myself of what to do. This is telling me, see this? I started with 0.1 and I ended with less. So this is telling me that I'm going to use that guy up, which means I must be using this guy up, which means I must be making more of this side of that arrow. Okay, so if I'm using up this side of the arrow, I must be making more of this side of the arrow. So plus, plus, minus, minus. Okay, so what value goes in here then, right? What value goes in here? Well, if I started with 0.1 and I ended with 0.26, I must have 0.0, I'm not enough space here, 0.038 moles per liter. Okay, so I must have used up 0.038 moles per liter of that in order to make that. And if that's the case, then I must have also used up 0.038 moles per liter of that stuff too, because they're a 2-to-2 ratio or a 1-to-1 ratio, right? So that applies there too. Oh, and here's another ratio. This is saying 2-to-2. So I must have added 0.038 moles per liter of that one. And this is half of those ratios. And so this is going to be 0.038 times 1/2, half of it. Okay, that means that in my equilibrium column, I'm going to have 0.6 for the hydrogen over there, 0.05 minus that, and I'm going to end up with 0.012. Here I'm adding them, so I'm going to end up 0.138. And here I'm taking the 0 and adding that value, and so I get 0.019. Now I have all of my equilibrium concentrations, and I can plug them all in. So here I have, that value is already there, so I have 0.12 squared, and then I have 0.19, and then I have 0.138 squared. Now I've plugged that in my calculator. My final answer is 1.50 times 10 to the power of 3. Wowzers, that's a huge K value. That's relying very heavily on my products there as it's written. Okay, that's a nice table. Let's do one more example. Okay, this one's slightly different. So here's my equilibrium. And 2 moles is placed in a 500 ml flask. So I can't, in this ice table, I have to put concentrations. Okay, so I can't just put my 2 moles in there. I have to go, oh, 2 moles in 0.5 liters is a 4 mole per liter solution. So initially I placed that much, right? I started with that, I put it in. So initially I have 4 moles per liter of my reactants, that one and that one. These are 0. And then it changes and I reach equilibrium, and it gives me, the question gives me no more information. It does not give me one of these like it did last time. So I kind of feel stuck as a student, right? Like, oh my God, where do I go now? Well, I know I can write an expression. Okay, so products over reactants, all gas, so I include them all. And I've been given a K value of 4.2. So here, the question is, what is the equilibrium of hydrogen? No, of each substance. What is the equilibrium of each substance? So it's wanting, what is this, what is this, what is this, and what is this? Okay, so if I have 4.20, and I know, like, I'm stuck. So I have to do a bit of algebra here in my column. I know that this is going to be reacted, and this is going to be reacted, and I'm going to form this, and I'm going to form this. And I can see that they're all 1-to-1 ratios. So when I react an X amount of that, this is going to react an X amount of this as well. And this will form 1X, and this will form 1X of that, because it's all 1-1-1 ratio. If this was a big 2 there, then that would be a 2X, okay? But it's not, so I'm going to erase it. Okay, so now I know that this is going to be 4 minus X. I know that this is going to be 4 minus X. I know that this is going to be X, and I know that this is going to be X. So now I can plug all these values, all these X's into this expression, and maybe I can solve for X. So my 4.2 is going to be these products. X times X is X squared. Divided by these, so 4 minus X squared. Now, I kind of am looking at a quadratic here, but we're going to leave those up to the mathematicians, and there's a shortcut we can follow here. If I square root both sides of this equation, it cancels out my quadratic problem. Woohoo! So So what I'm left with is square root of 4.2. So the square root of 4.2 is 2.05 is equal to x over 4 minus x, right? Square rooting both sides there. Okay, now I need to solve for x. Now this takes a bit of algebra. Okay, so now I need to solve for x. So this is going to be 2.05 times 4 minus x equals x, and multiply both sides by 4 minus x. Then I need to distribute this into both sides. So this is going to be 8.2 minus 2.05x equals x. Now I got to combine my like terms. 8.2 equals adding 2.05 to both sides. This is going to be 3.05 x's. And then dividing both sides by 3.05, my x is going to be 2.69. Now, don't stop there because this isn't math, right? So even though my value is for x is that's not necessarily the equilibrium concentration expressions. So x of 2.569 is equal to my H2 concentration, and it's equal to my, and it's equal to my carbon dioxide concentration, okay? And this would be moles per liter for concentration. But for my concentrations of these guys, it's 4 minus x. So 4 minus the 2.5, or 2.69, I mean, is 1.31 moles per liter, is equal to my carbon monoxide and my water, again, with the equals, which also equals my water vapor concentration, because those are 4 minus the 2.69, which equals the 1.31. Okay, so that's about as hard as ice tables get. I already have the expression. I'm trying to figure out what my equilibrium values are, and in that case, I got to plug in a bunch of x's and solve for x within my expression.